Hello dear learners, welcome you all to the fourth module of the Swayam MOOC course on electricity and electrical wiring. This fourth module is based on fundamentals of alternating current. In this unit, we will discuss about different components with AC. This unit contains different components with AC. That is, we will go for using resistors, capacitors and inductors in different combinations with AC and see the variation of current and voltage. Let us first discuss an AC circuit containing only a resistance. This kind of circuit is said to be a purely resistive circuit. So let us first discuss a AC circuit containing only a resistance. So for this, let us consider a circuit in which only a resistive element is there. So for this, let us consider the resistor of resistance capital R to be connected to a source of EMF capital E. Then the equation is given by this. So equation 1 represents the equation of alternating EMF in case of a AC circuit containing only a resistor. So such a circuit is said to be a purely resistive circuit. Let I be the current in the circuit at any instant of time t. Then the potential drop across the resistance R will be IR. So in this circuit, the instantaneous EMF of the source will be exactly equal to the instantaneous potential difference across R. So therefore, we can say that the EMF E, which is equal to E naught sin omega t, is exactly equal to IR. Therefore, the current is equal to E naught sin omega t divided by R. So E naught by R is nothing but the maximum or peak value of current in the AC circuit. So the current is I equal to I naught sin omega t. So in the previous slide, by comparing the equation 1 and 2, we note that both EMF and current are functions of sin omega t. Hence, the EMF E and the current I are in the same phase in a purely resistive circuit. This means that both E and I attain their zero, maximum and minimum values at same respective times. So this is the phase diagram for the resistive circuit containing only a resistor with the AC source. We are moving to the another kind of AC circuit where only an inductor is present. So with an AC source, only a inductor of inductance capital L is connected. For such kind of circuit, the equation of the alternating EMF is given by E equal to E naught sin omega t. We assume that the inductor has negligible resistance. Thus, this circuit is completely inductive AC circuit. As the alternating current flows through the inductor, a back EMF is set up which opposes the applied EMF. Therefore, the net instantaneous EMF will be equal to the EMF minus the EMF due to the opposition of the back EMF. But in case of such a circuit, the EMF must be zero because there is no resistance in the circuit. Therefore, we can equate this equation to 0. Therefore, E is equal to L di by dt. So from equation 3, we see that this EMF should be equal to this instantaneous EMF. As the applied EMF is sinusoidal, we expect the current also to be sinusoidal. Thus, the average current must be 0 over a period of time. So if we integrate, we see that the current comes out to be this one. On comparing the equations in the previous slide, we can conclude that the phase angle of current is pi by 2 radian less than the EMF. So here you can see in the phasor diagram, this is for EMF, and this is for the EMF phasor, and this is for the current phasor. So their current is lagging by a phase of pi by 2 with respect to the EMF. Thus, in case of an inductive AC circuit, the voltage is ahead of current by a phase of pi by 2, or you can say the current lags behind the voltage in phase of pi by 2. We are moving to another circuit in which only a capacitor is connected to an AC source. So in the circuit, only a capacitor of capacitance C is connected across a source of alternating EMF E. So the equation of the EMF is given by this equation 5. Due to the continuous surging and discharging of the capacitor plates, a continuous but alternating current exists in the circuit. At any instant of time, the potential difference across the capacitor plates will be equal to the applied EMF. So if we go for a calculation, then we see that the current at any instant to be this one. So this is the equation for current at any instant, where I naught is the current amplitude or maximum current obtained in the circuit. From the equations and observing the phasor diagram, we can see that in a capacitive circuit, the current leads the voltage, or voltage lags behind the current in phase by a phase of pi by 2 radians. Now we are going to discuss about the AC circuit containing a resistance and a inductance. For this, let us consider a circuit in which a resistor of resistance R and inductor of inductance L be connected in series to a source of alternating EMF capital E. The equation for this is given by E equal to E naught sin omega t. Let I be the current through the series circuit at any instant. Then the voltage across R will be equal to voltage vector R is equal to Ri. This voltage will be in phase with current. As we have studied in the previous slide about the resistive circuit, in which we have seen that the voltage and current are in phase with each other. Similar to that, in the part for the resistor, the voltage will be in phase with current. Thus, the phasor VR and the current I is in the same direction. So here you can see in the figure the phasor VR, that is voltage drop across the resistor, and the current, they are in the same direction. The voltage across the inductor L is given by this relation, which is ahead of current in phase by pi by 2 radians. So the phasor for the voltage across the inductor lies pi by 2 radians anti-clockwise with respect to the phasor current I. So this is the amplitude of the voltage across the inductor. So by calculating, we see that the phase angle between the resultant voltage and current is given by this relation. So from the phasor diagram, it is obvious that the current lags behind the EMF by a phase angle of phi, so that the instantaneous value of current is given by this equation. We are moving to another kind of circuit in which a resistor and a capacitor are connected in series with the AC source. So let us consider a resistor of resistance R and a capacitor of capacitance C be connected in series with a source of alternating EMF capital E. For such a situation, the equation of the alternating EMF is given by this equation, E equal to E naught sin omega t. Let I be the current through the series circuit at any instant. Then the voltage across R is given by this relation, V is equal to Ri. So the phasor VR and IR always in the same direction. So this is the amplitude of VR. The voltage across the capacitor of capacitance C is given by this equation. So this voltage is behind the current in phase by pi by 2 radians. So the phasor of voltage across the capacitor lies pi by 2 radians clockwise with respect to the phasor current I. So this represents the amplitude of the voltage through the capacitor. So by calculating, we can go for finding the phase angle between the resultant voltage and current given by this. So from the phasor diagram, it is obvious that the current is ahead of the EMF by a phase angle of phi, so that the instantaneous value of current is given by this equation. Let us go for another kind of circuit in which an inductor and a capacitor are connected in series with an AC source. So, a capacitor of capacitance C and an inductor of inductance L are connected in series with a AC source of EMF E. So the equation for the EMF is given by this. The voltage across the inductance is ahead of current in phase by pi by 2 radians, while the voltage across the capacitance C given by this equation is behind the current I in phase by pi by 2 radians. So the phasor for voltage across the capacitor lies pi by 2 radians clockwise with respect to the phasor current. So by calculating, we can go for finding the phase angle between the resultant voltage and the current. It comes out to be this one. So from the phasor diagram, it is obvious that the current is ahead of the EMF by phase angle of 180 degree. So this is the equation, which means the instantaneous value of current in case of a circuit containing an inductance and a capacitance. So this is the phasor diagram for the circuit containing inductance and capacitance. Let us move to another kind of circuit which is used in many practical applications, which contains an inductor, a capacitor and a resistor in series with an alternating EMF. Suppose a resistor of resistance R, an inductor of inductance L and a capacitor of capacitance C are connected in series to a source of alternating EMF E. In such a circuit, the EMF is given by this equation. Let I be the current through the series circuit at any instant. Here, the voltage across the resistive element R is this one, which will be in phase with the current I. Thus, the phasor for the current and the voltage across R are in same direction. The voltage across the inductance L is ahead of current I in phase by pi by 2 radians. Therefore, the voltage phasor for the inductance lies pi by 2 radians anticlockwise with respect to the phasor current. Similarly, across the capacitor, the voltage will be this one, which is behind the current in phase by pi by 2 radians. Thus, the voltage phasor across the capacitor lies pi by 2 radians behind clockwise with respect to the phasor current. So if we go for calculating the maximum current in the circuit containing L, C and R, then it is found to be like this, which depends upon the value of resistance, the value of inductive reactance and the value of capacitive reactance. The relationship between the resistance R, inductive resistance XL and capacitive resistance XC and impedance Z is called the impedance triangle. Here you can see the phasor diagram for the circuit of AC source containing inductance, capacitance and resistance in series. So we can see that in case of such a circuit, if the value of inductive resistance is more than the capacitive resistance, in that case the LCR circuit is said to be an inductive circuit. If the value of inductive resistance is less than the value of capacitive resistance, in that case the circuit is said to be capacitive circuit. And if these two are equal to each other, then we can see from this equation we can see if the value of inductive resistance and capacitive resistance are same, in that case this term will go to 0. So the circuit remains as a purely resistive circuit. Now we are moving to the resonance condition of a series LCR circuit. So in case of an LCR circuit, the resonance condition occurs when the inductive resistance is exactly equal to the capacitive resistance. So the frequency of resonance is given by 1 by 2 pi root over LC, where L is the value of the inductance and C is the value of the capacitance. In case of the resonance condition, the current in the circuit is at its maximum value. So it has power factor of unity. This kind of circuit functions as filters, and this kind of circuit also act as acceptor circuits. Let us now discuss what is the sharpness of resonance. The sharpness of resonance is a measure how quickly a resonance system returns to equilibrium after being disturbed, and this can be measured with the help of the quality factor or Q factor, which depends upon damping and amplitude of vibrations. The sharpness of resonance increases or decreases with an increase and decrease in damping. So this figure shows the bandwidth of a series resonance circuit. The bandwidth can be expressed as the difference between the edges of two frequencies, that is F2 and F1, and from this we can go for finding the quality factor in case of a resonance circuit. So the quality factor of series resonance circuit is the ratio of resonant frequency to the bandwidth. So dear learners, we have come to the end of this session. So here's some quiz are designed for you. So I hope you will enjoy this quiz. Thank you for your patience. Hope you have enjoyed this session.